So in my last video, I posed a question for experts or just anybody. The point of the question was to help help the other person understand why I'm excited about gravitational redshift. Unfortunately, I don't think that I don't think it went over as well as I had hoped. Um, the question is on the screen. If the universe were exactly the same as it is now, but static and infinite in all directions of space and time, would there be an observable limit caused by gravitational redshift? Not expansion, but would there be an observable limit because of gravitational redshift? Now, if you're an expert, I don't know exactly how you'll answer this. There's a couple of different ideas floating out there, but there's not much to this. There's not much about this. Gravitational redshift is considered very insignificant. It's considered at the star and the galaxy level, not anything more than that. My proposal is that that gravitational redshift is depends on the length of or the distance of light travel. So the reason that I think that is because it includes a larger and larger area. Let me just show you an animation. Where is that tab? Alright, so here, this is just a growing circle. And I call this the sphere of influence, or the region of influence. Is what this is as light. Let me back up to the very beginning. Alright, so that's going to be difficult. I don't want it to play when I rewind. There we go. Alright, so wherever, I don't know where the center is, but wherever the center of this is where the star is. So the star releases light. It goes out in all directions. Depending on where it's observed, if it's observed in some part of space that has a lot of mass, like near a black hole or something, then it won't be a redshift. This is only when it's observed in a location that has a less amount of gravity as than the star. So it's only when it's observed uphill. So when the light has to travel uphill, is going to be a redshift. And the region depends on the length of the light wave or the distance of light travel. So as it, like say this would be the observer right here. All the observers are on the outer edge of this, looking at the star, and this is the entire region of gravitational influence on the light. Just like with the dust cloud in the earlier example, or in the example in my last video. I think I have an image I can grab real quick. So you have this is the Earth and this is the Sun, and you have a dust cloud around the Sun. As the light wave travels outward, if you have an observer here, 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 if you have observers all along the length of the light wave, a larger and larger amount of gravity will influence it. And so each distance away from the star, there's more gravity, more mass influencing the space-time around the object, and so there's a higher redshift. Birkhoff's theorem is what it implies, that it all goes to the center of the star. All the mass is this. It's as if all the mass is in the very center. Now, Birkhoff's theorem requires symmetry. So that was the whole point of these 3 points in my last video. That symmetry manifests at scale. Birkhoff's theorem is applicable in symmetrical scenarios. But the other important point is the structure of the universe is hierarchical. And what I mean by this is that the mass density is equal to it's inversely proportional to the radius of the region in question. So I developed a calculator for this. I'll go over that. But I did want to bring up, somebody made a comment on the last video, and that's why I made this video. They claim to be an astrophysicist. Let me just pull up their comment here. They claim to be an actual astrophysicist, but they didn't address anything I've said. They just said, this is way off the mark. These lines are shifted the further away you get from the observational point, in our case the Milky Way. We know how far these things are due to a few factors such as standard candles with type 1a supernova, as well as galactic size measurements, where the galaxies are the same size appear smaller because it's further away, and if it's half small, all he's explaining here, or all, I don't know if it's a man or a woman, all that they're explaining is that there's a distance proportional redshift. Now, they say we can also measure the apparent redshift and find out the velocity of the galaxy. That's an interpretation. That's my point. You're basically saying the universe is expanding because it's expanding. It's the velocity of the galaxy is an interpretation. It could be the mass of the region is affecting it. It could be the gravitational redshift. There is no difference. You can't tell. You can't look at a redshift and be like, oh, that's gravity, or oh, that's velocity. There's no difference. Both produce a redshift. Now, this calculator I made, I think, will kind of help this. You'll help you understand this cosmologically speaking. The inverse mass density is important because if you just use mass density estimates for the entire universe, that doesn't work because it's not enough. Mass density is scale dependent. So the density of the region that you're talking about is lower the larger the region, and it's higher the smaller the region. So here's an example. In this circle right here, this is 114 megaparsecs. The observer is on the outside and the emitting star is in the center. Okay. As the light wave travels outward, there's more and more mass in this circle. Okay. So the more and more mass that's in here, the larger and larger the redshift. Now I've got the observed frequency, emitted frequency, then I've got the 1 plus z from recession velocity and 1 plus z from the gravitational redshift. They're the same thing. Okay, it's one is interpreted as recession velocity, one is interpreted as gravitational redshift. My point is that they're the same. It doesn't matter. It's because the mass density decreases as this gets larger. So if we go up to 1,000 megaparsecs, this includes a larger sphere of influence, but the mass density is less. The reason that's important is because it continues getting less until you get to around this 4152, something like that. I think that's the last as far as we can go before it breaks. Maybe we can go a little more. Oh, we can go a little more. We can go higher. There we go. 4164. So it does depend on your starting parameter for the Hubble parameter. Now again, Hubble parameter, this is just an interpretation. This meters per second per megaparsec. This just shows you the amount of redshift when it's interpreted as velocity. This you can also interpret it as gravitational redshift, which is what we're doing here. And so when you get to this 4163 megaparsecs, you get to the Schwarzschild radius, and the Schwarzschild radius is the observable radius, okay? And that's when this density is the lowest. That's when the mass density is the lowest. And so the density at the observable radius, for basically the mass density of the entire observable universe, is the same as it would be in the FLRW metric or in mainstream cosmology. But you can't use that for the smaller scales because it's not accurate. So this mass density is not accurate on the scale of 1,000 megaparsecs. Or let's say 500 so you can see the circle. So the mass density at 500 megaparsecs is this right here. It's a lot less, or it's a lot more. It's a lot higher. The reason this is important is because cosmologists have considered gravitational redshift before. They just don't think it's enough. The reason they don't think it's enough, and it doesn't produce that linear, or not linear, it doesn't produce that distance proportional relationship, is because they're not using an inverse mass density. Mass density depends on the region of question. Man, I don't know. The reason is because there's a hierarchy to our universe. So you have stars; they're extremely dense. Then you have galaxies. They're not as dense, but they're more dense than stars, or they're less dense than stars, but more dense than the observable universe. That's for sure. So you have stars, galaxies, clusters of galaxies, superclusters, veins, filaments. All of these things produce gravity, and they all have mass, and they're hierarchical. So the smaller scales have a higher density. The larger scales have a lower density. This is very important in order for the gravitational redshift to work out, but it does work out. This is the reason that I posed the question. Okay, the reason that I posed this question. If anybody can answer this, it's going to be the same as the observable limit if the universe is expanding. Or it's going to be this. I mean, it depends on what you're talking about, and there's all kinds of ways of describing things, but it could also be the age of the universe. So 13.7 billion light years. It depends on how you do it, but what do you calculate? And if you say that there's no gravitational redshift, or there's no observable limit from gravitational redshift, I think you need to reconsider. Objects are embedded. They're embedded within other objects. Anyways, I don't know. Nobody believes me. Nobody cares. I would love to have a conversation with an actual astrophysicist, not one that just makes assertions and interpretations without justification. Anyways, thank you so much for listening to this probably awful video. I don't know. Good luck.